Okay, so I'm recording. We are going to use our power series. It's gonna be dark outside. We're going to use our power series. We turn all the lights off.
No, we are sleeping.
Can I see what it looks like with all the lights off?
Yeah. I give permission.
So think way back to when you learned about geometric sequences and series. Do you remember the formula for the sum of a geometric series? Pop quiz.
XN. No. This is geometric. Not a sum. What are series?
Sum of a geometric series.
Well, geometric series is something N. And then you also have R because it's exponential. Yeah, but you also have N somewhere. Is it a per?
Is that what this smells like? No, it's not.
You remember? A geometric series is the sum. So the infinite geometric series is the sum from n equals 1 to infinity. A sub 1 is our first term. R is our ratio raised to the power of n minus 1. Our formula for that is that it's a sub 1 over 1 minus r. Please notice, this is the sum, the infinite sum of a geometric series. We already know that formula. So now what we're going to be looking at is kind of working backwards to understand if I can write this sum, if I can write this series, this sum, in the form of a geometric series, then I can figure out what it equals using what I already know. Okay, so here's my first example. If f of x is the sum from n equals 0 to infinity of 4x over 2 to the n, let's write out the terms so we have a basis for where we're starting. So our first term, everything raised to the 0 power, is just 4. Our second term, everything raised to the first power, we have 4. And then we have x over 2 to the first. Our next term, we have 4 x over 2 to the second, and it's going to continue with our exponents increasing. Okay, so if we are trying to find f of 1, we're substituting x in for each of those. So 4 plus 4 times 1/2 plus 4 times 1/2 squared plus 4 times 1/2 to the third. And this is an infinite series. This is a geometric series. In this geometric series, this is an infinite geometric series with a common ratio of 1/2 and our a sub 1 equal to 4. So our infinite sum is going to be a sub 1 over 1 minus 1/2. Or 4 over 1 minus 1/2. 4 divided by 1/2, 4 times 2, that's 8. And that's not an approximation, and I didn't have to do an integral or a limit. I'm just using my geometric sum formula. How are we feeling? It's not bad. Okay, let's try the next one. Let's find f of -1. So this is going to be our infinite sum, n equals 0 to infinity of 4, and I'm plugging in my x, -1/2 to the n. I went back to the original definition of f of x. We said here that f of x equals the sum, and then I expanded the sum. So for my first one, I used the expanded form, and I said, oh, it's a geometric series. For my second one, I already know this is a geometric series, so I'm going to leave it in the summation format, and I'm going to notice that this is an infinite geometric series with my common ratio equal to -1/2, which means that my infinite sum is going to be my first term. Oh, I should probably figure out a couple terms, huh? So my first term, when I plug in 0, I end up with 4. My second term, when I plug in 1, +4 times -1/2 is -2. My next term, when I plug in 2, I get 1/2 squared. It's going to give me +1. This is going to be alternating as I go, which is fine.
Oh, yeah, I think so.
Okay, so my infinite sum is going to be my first term over 1 minus my ratio, -1/2. 4 divided by 3/2, or 8/3. Okay, let's find f of 1/2. Same idea. I'm looking for my infinite sum from n equals 0 to infinity of 4. 1/2 divided by 2 is 1/4 to the n. So my infinite sum is my first term 4, 1 minus 1/4 in my denominator, 4 over 3/4, which is going to give me 16/3. We're doing okay, right? Okay, so let's look at f of 2, and then we're going to extrapolate and find f of x. Two divided by 2 equals 1. So for this one, we have our infinite sum is our first term divided by 1 minus our ratio. Oh. Uh-oh. What does this tell us?
Indeterminate.
It diverges, which we knew. 1 to the n diverges. 4 times 1 to the n diverges. You could also think about this. It's 4 plus 4 plus 4 plus 4. That's our series, right? This diverges. We cannot find that. Okay? So now we're going to find our f of x.
Is that also because r is greater than 1? Or
It's greater than or equal to 1. Yes.
Oh, yeah.
So for this, we have our sum from n equals 0 to infinity of 4 x over 2 to the n. Our initial term, remember when we wrote this out at the beginning, it was 4 times x over 2, 4 times x over 2 squared. We wrote that out way back at the beginning. Our common ratio, what's being multiplied each step of the way, is x over 2. Our initial term, it's still there, it's just behind the box. Our initial term, our a value, a sub 1 is 4. It's behind all the calculus books. Slide those out of your way. So we can use our formula and let's simplify that so it's not a complex fraction. I'm going to multiply everything by 2. So I get 8 over 2 minus x. That's what this function actually equals. And if you want to test me, I can prove that this is true. What does f of 1 equal if I plug into 8 over 2 minus x? It equals 8. And I can verify it. It matches with this one. Do you believe me for all of it? Even for f of 2. F of 2 is undefined. Diverges. This is null set. Undefined. F of 1/2 I can figure out. F of 1/2. 8 over 2 minus 1/2. That also equals 16 over 3. I can verify that this matches every single one from up above. So, if we can rewrite a function in in a geometric notation, we could actually rewrite it as a series. So now we're going to reverse it. If I can write this as a constant over 1 minus r, I can rewrite this in a summation formula. So this one actually is kind of nice because it's all lined up for us. A1 is 2, r is 3x, and I can say that f of x equals the sum from n equals 0 to infinity. Oh wait, 1 to infinity. No, 0 is fine. Of 2, 3x to the n, which is the equivalent of 2 plus raised to the first power, so 6x, plus 3x to the second power, 9 times 2 is 18, x squared, plus raised to the third power, 27 times 2, we got 54, x to the third, and so on.
Why is it -1 in the original equation for this one?
There's two different ways to do it. So you can write it as this way, or you can write it, if you shift the lower index, it's the sum from n equals 0 to infinity, a sub 1, r to the n. Same thing.
Okay, I was just wondering what you said.
I just added 1 to both of those, and that's all.
It was the n equals 0.
Yeah. Let's talk about the radius of convergence. So what are the rules for geometric for the radius of convergence? In order to converge, it has to go between, the r value has to be between -1 and +1, right?
Yes.
So we knew that -1 is less than 3x is less than +1. I'm going to move this off to the side. Oh, that's our halfway. After this, we'll do a brain break. -1 is less than 3x is less than +1. And if we were to solve that, we'd get -1/3 is less than x is less than +1/3. And that's this is our interval of convergence.
Okay, hang on.
Holding on.
So this is the interval where the values will converge when you plug in, like,
So if you plug in x's that are outside of that, we no longer have a converging series.
it would diverge. That's not the same thing as like the copying thing that we were doing before.
Correct.
The thing we did on this thing. It was like it turned out that it was like sine along. Or it's the same thing.
So right now we're still just working with series and like manipulating them and trying to understand them. We haven't started trying to like replicate another function yet. Now we're kind of working backwards to show you. See that function? I could replicate that function with a series. They're exactly the same thing. But we'll get to the approximating in a couple of sections. Okay, I'm going to pause the video and you guys are going to get a brain break.